So in this video we will be concerned with calculating these elements of the shift operator. Actually we will be calculating numerically by some relatively easy to program method all elements, not just the zero ones here. Well, the trick is that we will again diagonalize this problem. That is, we will solve this problem in a different basis than the n1, because in there we know that, or we kind of expect that the D operator is not going to be diagonal. We first verify that it's not diagonal. It would be stupid to do a transformation if it's already present for us there. So this is an exponential of minus q0 divided by square root of 2, and here we have the difference of the creation and annihilation operator. So in order to for this to be diagonal, the diagonal would have to be this operator in here. So we would have to have the n a dagger minus a n thing, the only thing that is non-zero. So the question is, what is this? And one can quite easily find, let's say, applying this annihilation operator on n would lead to square root of n minus 1 here. That's this thing. Creation operator gives me the square root of n plus 1 and n plus 1 plus, sorry for this mess. So that was obtained by action of these operators to the right, and from the left, let's make some space here. From the left we have the n coming on this. So altogether I see n meeting n plus 1, this is 0, n meeting n minus 1, this is 0. So this is 0. So I haven't even looked at the non-diagonal elements here, but I can say that this operator is all but diagonal. This is not diagonal. That means the exponential of it is also not diagonal. But nothing can prevent us from well, this is a impulse. It's a momentum, a Hermitian operator. This has to be diagonal in some basis. So nothing can prevent me from defining an operator z, which is equal a plus or a dagger minus a. Well, I can diagonalize it. This I can do by means of some so far unknown but numerically very easily findable transformation, which looks like this. So this is now diagonal, and using that I can well, that's a thing that I can diagonalize, and then once I diagonalize it, I can kind of transform the whole operator back again into my original basis. So the whole trick will be in writing the exponential of minus q0 divided by 2 a dagger minus a in a following way. So exponential has to be done on the diagonal operator. So it will be done on this one, and once I'm done with this exponentiating, I will turn everything back to the original basis. So this is it. Now I need, in order to apply this effectively numerically, I need one more observation, and that observation is the following. If I take the potential energy surface of the harmonic oscillator, I see that the wave functions, so this is the ground state, here is the first excited state. This is how the wave function would look like. I'm actually sort of drawing it with a little bit of experience of how they should look like. You see that they are less and less confined. So the ground state is the most confined function. This is really concentrated only around the bottom here, but let's say the third one already extends a little bit farther. And you know, the intuition is that if I'm expressing a function, for example, if I'm expressing a function which is not shifted at all, I need just one wave function of all the functions that are available in the harmonic oscillator. If I shift a little bit, I need a little bit more of an extent. So want to, let's say, express this function. So of course this is still very similar to the original one, but I will also need to include some of the other wave functions. And because the extent of this wave function away from the zero here is not very far, I will not need many of these wave functions. I will only need the very high quantum number wave functions when my initial, or when my oscillating function extends somewhere far away. This means that if the shift is not too big, I will not need many states to represent my new wave function. Or put it in another way, the more away from the center I want to be, the more states I will need. But I can kind of count on that at the beginning I will need, with small shifts, and we only need this for some demonstration, with the small shifts we will not need many wave functions to represent this. Alright, that means I can limit my space of wave functions to some finite number, and all these matrices, the matrix C for example, will be finite. So I will do the following. I will say the Z is equal to some matrix. This is a matrix which has n here, let's say 20, and that represents everything I need, or basically this n is already too much. Yeah, so I diagonalize this big matrix. I diagonalize it, make an exponential out of it, turn it back to, well, calculate the shift operator. So I calculate the shift operator the same way. So there will be, probably this is not going to be diagonal, obviously. So there will be elements all the way here, but they will become less and less important as I go farther away from zero. And then I do these transformations to be sure numerically on, let's say, n20 or 30, but at the end I know that I'm only representing some small shift, so I will, let's say, need 5 or 10 of these wave functions. So then I'll cut this relevant part of my operator out of this big matrix, and everything else, all the calculations later I will be using with this smaller matrix, which is enough to represent my wave function. Why I'm doing this, why I need more states? Well, I need more states only because in this operator I have to have for that transformation also functions that are up here well represented. For that means I need to include in that wave function not just this block that I will be using later, but also other things somewhere farther away. All these wave functions that are cut away here, I don't need them to be well represented. They are useless. But these ones up here on the diagonal, I will need them to be represented well. So that's why I need to start with something much bigger. Okay, so the algorithm to calculate my D will be the following. So algorithm. It's nothing really scientific. So you start with create an operator Z, which is equal to A dagger minus A. This is very simple because I know the matrix elements of these guys. I know how they act on the states, on the number states. So this I forgot here in the number state basis. Number state is in this case this specifies the number of phonons, quanta of the vibrational energy in that state. So second point is diagonalize the matrix Z. Then third is to calculate exponential of that diagonalized wave function with some prefactor, which is extremely easy because it's just exponentiating the diagonal elements. Then transform back. Five is well, cut the number of states. So cut the number so alright, so this we create with, let's say, with some n maximum equal, I don't know, 20 for example, but these are just orientational numbers. So and here we cut the n max to say 8 or something like that. This has to be done by some, or has to be checked by some convergence criterion. 6.6 will be, well, now I'm already going towards the dynamics. So from now on, this is the dynamics that I want to calculate. So we will calculate in the 6 we will calculate the initial condition, which is well, that's the psi 0 equals now the exponential, or this operator that we have just calculated, a plus minus a, so that's the z acting on the 0. That is basically what we need. Or in case that we would use this expression here, the initial one, we can essentially just take these elements and nothing else we done. Well, that's basically what was done here. We will be interested in those elements, so we'll just take those elements. This is what we were looking for, and everything now on from this will be about how we turn this into the dynamics that we can plot on the screen.